And we are back to the cart and timer tape. Our task today is to figure out how much weight we need to drop to accelerate the cart in order to overcome the friction that happens when the cart rolls. So hopefully, if we have just enough weight on here to counteract the friction, we shouldn't actually see any acceleration. We should just see the cart go at a constant velocity. Here's an interesting thing about friction. The force of friction when something is not moving, static friction, is actually, it can be higher than when the object is moving. So it's perfectly feasible that this 30 grams here, we have a 10 and a 20 gram weight both dangling here. It's possible that that won't be enough weight to start the cart, but if we just give it a nudge, it'll be just enough weight to keep it going at the velocity we started at. So hopefully if we just give it a little nudge, it'll keep going the same speed. It looked pretty good, but how can we be sure that that was a constant velocity? Well, we have our timer tape here. We got our timer. We know that if something is going at a constant velocity, there will be a constant distance between the dots that come out, as long as every dot is put out 1/60th of a second after the next. All right, let's give it a try. Okay, our cart's not going anywhere. I'm going to start the timer and give the cart a little bit of a nudge. I'm going to try that again from a slightly different location on the table. We may have a slightly different slants on the table at different points. Here is what our dots look like. They were very, very close together at first. I nudged it only to a very low velocity. It wasn't fast enough. And you can see here's where I nudged it again, and it got up to, it looks like a constant velocity because there's the same distance between these dots for a while, and then it mysteriously started to slow down. You can tell because the dots got closer together, and it came to a stop. And then we tried it again, and it looks like there's about the same distance between dots for a while, and then again the dots get closer together, so it slowed down just a tiny bit, and then we stopped it at the end. So this looks pretty good to me, because this is a very slow velocity. So the dots becoming just a little bit closer together is really a very slight change in the velocity, and it took several seconds for that to happen. So if there is a slight change in the velocity, it's very, very small. And the good news is that the cart actually kept moving for a while. So I think we found that our 30 grams is exactly what we need to keep the cart moving. And we may not have gotten a perfectly evenly spaced dots because that table might not be perfectly level. But I'm going to go ahead and say that the 30 grams is the perfect amount of weight to exactly counteract the force of friction that is acting backward on this cart. And it would be incorrect to say that it was 30 grams of force, because the force that the 30 grams applies is the number of kilograms times 9.8 meters per second squared, which is the acceleration of gravity. So it would be 0.03 kilograms times 9.8. That would be the actual force in newtons provided by those weights. And also, that would be the same number of newtons of friction that is pushing backwards on this cart while it's moving. We need to know exactly how much mass was accelerated. What was accelerated? Well, everything that was moving. So let's just drop all this stuff on the scale. Here's our 200 gram weight. Let's see if it's actually 200 grams. Oh goodness. That's not exactly 200 grams. You guys should account for that discrepancy. Let's see. Our cart. Oh good, we didn't overload the scale yet. Alright. The string was moving. It was accelerating because it was changing its velocity. I'm going to try to pile all this stuff on here. Good enough. Are we forgetting anything?